Welcome everyone to this explainer. Think of this as your personal masterclass in architecting data systems. I am so thrilled to be your guide today as we equip you with the absolute essential skills of a data engineer. And we're going to demystify exactly how to build scalable, robust data pipelines on the Google Cloud Platform. So whether you're completely new to the cloud or you're just looking to really solidify your architectural fundamentals, we have a fantastic syllabus lined up for you. Right off the bat, I want to start our class today with this rather jarring industry reality. 80% of the effort goes into collecting, cleaning, and transforming the data. Look, if you've ever stared at a beautifully designed, highly predictive machine learning dashboard and wondered how it actually works, well, the secret is that the heavy lifting happened long before that dashboard was ever built. Without proper data engineering, your downstream systems fail, queries crawl to a halt, and business users lose total trust in the numbers. Honestly, that is exactly why data engineering is arguably the single most critical role in the data sciences world today. So here is our syllabus for the day. 1. Intro to data engineering. 2. Mastering big data concepts. 3. Designing the data warehouse. 4. Batch, streaming, and lakes. And finally, 5. Machine learning and optimization. Okay, lesson 1, intro to data engineering. Let's dive into it. Before we can even start building, we absolutely have to understand the core problem we're actually solving here. Picture a traditional bank for a second. They might have a highly specific system just for credit cards, another totally separate one for mortgages, and yet another for customer service. This creates what we call data silos. So let me ask you, how does a CEO answer a very basic business question about total customer value when the data is trapped across 5 completely independent systems? Spoiler alert, they can't. A data engineer's very first mission is breaking down these silos so data can actually be centralized and analyzed. To actually move that data, we rely on 2 primary pipeline methods, ETL and ELT. Now, notice the subtle swap of the T and the L there. Are you transforming the data before it reaches its final destination, or are you loading it completely raw and transforming it later? It sounds like a minor detail, I know, but the crucial point here is that this simple order swap completely dictates your technology choices, your system performance, and ultimately your final cloud bill. In modern cloud environments like GCP, ELT is actually often preferred. Why? Because cloud data warehouses have massive, virtually limitless processing power to transform that data after it safely lands. Lesson 2. Mastering big data concepts. Shifting our focus now from what is big data to how do we actually process the stuff, we really need to understand the core secret of big data storage. Think about it. How do you store a 1 petabyte file when your standard hard drives are only, a few terabytes? Well, you don't store it in one place. Instead, a massive file is broken down into small 128 megabyte chunks. These file parts are then distributed, essentially at random, across a massive cluster of multiple machines. And a smart metadata layer simply keeps track of where everything lives. But here's the catch. Once your data is scattered across all these different machines, how on earth do you perform a simple operation, like a basic word count? You can't just read straight down a single document anymore, right? This requires something called MapReduce. Your system literally maps the distributed file parts, shuffles the data across the network to group similar items together, like apples with apples and bananas with bananas, and then reduces them to give you a final, unified count. Now, time for a quick reality check when you're operating in the Google Cloud Platform. We so often think the absolute only limitation in the cloud is our budget. But as a real data engineer, your responsibility is also to manage quotas. These are the default limitations placed on services just to prevent complete system overloads. Let me tell you, understanding your boundaries in the cloud is just as important as writing good code. Moving right along to lesson 3, designing the data warehouse. So now that we actually have our data centralized, we have to model it. At the beating heart of our data warehouse are fact tables. Think of these as the absolute core measurements, things like the total amount of a daily transaction. And then surrounding these facts, we build out dimension tables, and those provide all the rich context, like the specific store location or the customer's demographics. When you are designing this architecture, you're generally going to face 2 opposing philosophies. First, the InMod method. This takes a very strict, top-down approach, really emphasizing absolute data consistency across the entire enterprise. But in today's incredibly agile big data era, the Kimball method often wins out. It is a bottom-up approach that prioritizes answering the end user's immediate business questions first, and that allows us to build the warehouse organically as new data continuously arrives. Within those philosophies, you also have to decide exactly how to structure the tables themselves, normalized versus denormalized. Normalized tables are brilliant, absolutely brilliant, for saving storage space and maintaining type consistency. But remember what we talked about with distributed big data systems? Combining, or what we call joining, tables across a network is a highly expensive computational operation. So sometimes a denormalized table with a bunch of duplicate data is actually preferred just to avoid those costly joins. Take a look at how this normalization process actually works in practice. By creating separate reference tables for categories like addresses or salaries, and simple linking them back to the central people table, we prevent the system from storing the text New York City a million redundant times. It is an incredibly efficient way to manage your storage.
Lesson 4. Batch, streaming, and lakes.
To get data into our beautiful new warehouse, we have to build pipelines. Try to imagine data as water flowing through a system. Upstream is your vast reservoir, and downstream is the kitchen sink where the business user finally consumes it. We have two main ways to control this flow. Over on the left, we have batch processing. This is where we group records together and process them on a set, predictable schedule, say once an hour or once a day. Then on the right, we have streaming, moving data in real time through managed services like PubSub and Dataflow. Now, while real-time streaming gets all the shiny hype in the industry right now, the cold, hard reality of our Masterclass is that 90% of organizational pipelines out there are still reliably running in batch. Before the data even reaches the structured warehouse, it very often sits in a data lake. The real beauty of a data lake, particularly something built on Google Cloud Storage, is that it treats absolutely all data simply as files. You can drop in highly structured tables, semi-structured JSON files, or just entirely unstructured data. And speaking of unstructured data, this is where things get really fascinating. When you're handling massive audio logs, for example, your lake can just store the raw voice files exactly as they are. From there, you might later run a process to extract the specific quality of a recording, the distinctness of a user's voice, or the overall crispness of sound, all just to feed into a complex speech recognition model. The data lake stores all of it effortlessly until you need it. Which brings us to Lesson 5, Machine Learning and Optimization. Okay, once we have expertly cleaned and warehoused our data, we can finally start predicting the future, all while keeping our system costs totally optimized. Let's build up your machine learning vocabulary for a second. When data scientists train their models, they are constantly looking for features. A feature is quite simply a specific column of input data that gets used for training. For example, if you want a model to predict whether it's going to rain tomorrow, your historical, humidity, and temperature columns are the features actively feeding that specific prediction. But listen, running complex predictive models and querying massive petabyte-scale tables in tools like BigQuery can get incredibly expensive. As a data engineer, cost optimization is quite literally your responsibility. You can optimize by clustering your tables, which physically sorts your data by your most frequently queried columns to save huge amounts of processing power. You also save serious money by moving old, rarely touched data to a much cheaper storage class like Coldline. And above all else, you protect the company by utilizing data loss prevention tools to automatically scrub personally identifiable information before it ever even hits the analytics layer. And naturally, that brings us right to security. I really want to emphasize this core tenet, the principle of least privilege. As a data engineer managing identity and access management in the cloud, you never, ever give sweeping universal access. You give a user, or frankly even an automated service account, only the absolute bare minimum permissions required to execute their specific job. Trust me, it is the absolute strongest shield you have against massive data leaks. So, as we wrap up our masterclass today, I want to leave you with one final exam question to ask yourself when you return to your own organization. Are you actually building a scalable, accessible data pipeline? Or have you just accidentally built a brand new, highly expensive data silo in the cloud? Focus on the real business questions, clean your data rigorously, and always build for the end user. Thank you so much for joining me in this explainer today. Keep learning, and I will see you in the next one.